Hi everyone, welcome to Vedantu English. I'm Diksha, your chemistry master teacher, and today we are going to do a very important topic from coordination compounds, right? But before that, let me know in the chat box if I am clearly visible and audible to all of you so that we can start with the topic crystal field splitting, right? And you know what is the interesting part? You have seen these stones, beautiful stones, right? That so many celebrities are wearing, right? Ruby, emerald, right? These stones, the color, the beautiful color of these stones is because of CFT, is because of crystal field theory, right? Crystal field theory will explain you why you have these colors of ruby is of red color, emerald is of green color. What is the phenomena that is responsible for this thing? And the interesting part is most of the things that we see are colorful, right? Like you're able to see, for example, this is a very like interesting quote that I have in my studio that is follow your dreams. So can you see these beautiful colors here? Right? These beautiful colors are actually because of CFT, right? So all the colorful things that you can see, it is because of CFT, right? So starting with our session with this beautiful quotation here, that is follow your dreams. And that is the reason you guys are here, right? Okay. So to follow your dreams, you definitely have to do everything in detail. And that is why I am here to take a lecture on CFT in detail. But guys, I have one, problem. The problem is that you guys don't do your homework, right? So only one student has done the homework for VBT, right? So very good sign, Nikki, that you have done your homework. Excellent. And this was the homework. This was based on VBT, right? And this I have given you detailed solution of this. Those students who attempted this but were not able to solve the question, you can go through this particular thing. First, you will solve the oxidation state. Then we know that CN is a strong field ligand. It will cause the pairing. And after that, what you will have is D2sp3. Now, here interesting part is that you have here D4. Now, the interesting question that you can have in your mind is, ma'am, why it's not like 1, 2, 3 fold and why it's not D3sp2? Because for octahedral, this will never exist. It can be D2sp3 or sp3d2, right? So that is why CN is a strong field ligand, but still here it is not pairing up because it is not required. Even if it gets paired up, this will remain empty, right? That's why it is not getting paired up, right? Okay. So that is the reason it has D2sp3 configuration, hybridization, and then there is magnetic movement. At one point, this will be shown by which, right? Here, magnetic moment is 1.7. That means number of unpaired electrons should be 1, right? So you have to find out where number of electrons are 1. This is the Cl, Cl strong field ligand, and according to that, you can see that in CuNH3, right? Already you have D9, so you have 1 electron that is unpaired. So that is why CuNH3 4 2 positive is going to show you 1.73 Bohr magneton as the magnetic moment, right? Okay. So you can do these questions yourself, right, everybody? And please, yeah, start doing the homework, okay? It's just very few months that you're left with. If you don't do your homework, I will not provide you with the DPPs. If you do the homework, if I see students, doing the homework, right? They are putting in the efforts, then I will also put in the efforts, right? Okay, I have already prepared the DPPs for you. All the lecture DPPs are already prepared. What I am waiting for is your input here, right? That you will show in the comment section by doing the homework. Just 2 questions I give you, right? You can do that easily, right? So, today we are going to discuss about crystal field theory. Let's discuss that in VBT we discussed that ligand is actually electron donor and metal is electron acceptor. Ligand is donating, metal is accepting, right? So we discussed here, as you can see this over here in VBT, we actually discussed that in the vacant d orbital, you can see the electrons of ligand, right? You can see over here. Electrons of ligand are donated in the vacant d orbitals. But what you will see in crystal field theory, there is no as such thing. It takes the interaction of ligand and metal as electrostatic interaction. And in the end, this will become the limitation of CFT, right? That it considered that it is an electrostatic interaction. That means it is an ionic interaction, right? So they discuss that we are taking metal as the cation and ligand as the anion, right? So metal is taken as the cation and ligand is taken as the anion. And that's how they are saying that there is electrostatic interaction that is between these two things. It is electrostatic model which considered metal ligand bond to be ionic purely from electrostatic interaction between metal ion and ligand. Now the question is that, ma'am, ligands are of two types, right? So here he has not considered about the positive ligand. They have not discussed about the positive ligand, and that is also one of the limitation of this theory. He has only given two things, that ligands if they are negatively charged, or ligands if they are neutral. He said that ligand, if they are negatively charged, we can directly take it as an ion, right? There is no big deal in that. Like you have Cn negative, you have F negative, Cl negative, right? All these are your negative ligands, and negative ligands we can take as anion, right? Anion point charges, right? Neutral ligand. Now, for example, you have NH3. Now we know that NH3 has polarity. We know that because of that polarity, N is minus negative. So that is why he said that from that side, right, whenever you talk about polarity, there is negative, there is positive. He said that this negative part will be donating to metal, right? So you will link the negative polar side to the metal, right? He talked about neutral ligands like this. So he justified that I am right and I am telling you right thing, that these are electrostatic interactions, right? So now in these cases, as I have shown you here, that negative ligand will be taken as point charge and the neutral ligands will be taken as dipole, in which negative polarity will be towards the metal, right? So ligands are treated as point charges in case of anions and dipole in case of neutral molecules, right? Next is, if you talk about the d orbitals, right? 5d orbitals you have. 5d orbitals you have, right? You always draw five boxes for d orbitals, d subshell, right? So whenever you draw this d subshell, we have also studied this in structure of atom, right? 1, 2, 3, 4. These are the 5 things that you have. You have -2, -1, 0, +1, +2. And we have also discussed about their 5 degenerate orbitals. Now, these 5 orbitals are of same energy, right? So, can I say they are same energy? When nothing is happening, they are of same energy. And same energy orbitals are called as degenerate orbitals, okay? So, you'll say that these are degenerate orbitals. Degenerate orbitals means they are of the same energy. And what is the name of these orbitals? Everybody in the chat box, write it down. dxy, dyz, dzx, then you have dx square minus y square, then you have dz square, right? Now, the shapes of these orbitals are very important in understanding the CFT theory for octahedral and for tetrahedral complexes, right? So, if you talk about this thing here, it's a very simple thing that these 5 orbitals are degenerate orbitals. Nothing is happening if I'm considering no ligand is approaching. Till now, there is no ligand that has approached them. No ligand is approaching, they all are same. It's like 5 friends, okay? 5 friends are like totally like, we will go together, we will, you are going to this tuition, I will also go to this tuition. You are purchasing this book, I'll also purchase. Some best friends are like this. You're taking non-medical, I'll also take non-medical. You're taking medical, they have no interest in non-medical, right? They're like, my best friend is taking non-medical, I'll take non-medical, right? Okay, guys, right? So we all have done this at some point of our life, right? So some students like, oh, you are taking commerce, I'm interested in science, but I'll take commerce, right? We're best buddies here, I can't leave you here, right? So it is like that. So they're always together, the energy is always same. No ligand is approaching. Now ligand will be that beautiful, beautiful, beautiful girl in the class. This is the ligand, okay? That is the ligand. Now we'll see that what will happen in the ligand, but firstly, we know that all the 5 friends, they have different nature, right? So these 5 friends will have different nature. So firstly, let's talk about these 5 friends here, okay? Firstly, let's talk about these 5 friends here. So dxy, dyz, dzx. These are between the x, right? These are between the x, right? Between x and y, this is the lobes are between the x's. Here lobes are between, this is dyz, right? This is dxz. So this is between x and z, right? So they are between. This plays a very important role, right? So if you talk about dx square minus y square and dz square, they are along the axis. Orbitals, the lobes are along the axis, right? So these 3 friends, even if the girl will, join their class, join their group, the girl will not be able to split these 5 friends all together. It's not like after the girl has joined, right? These orbitals will split like this, right? There is new girl in the class and they all will split like this. 1, 2, 3, 4, 5. No. Now also they will split in pairs, right? Always what you will see, even if they have to, they will split after some point, right? dxy, dyz and dzx. It will be together. Dx square minus y square and dz square, it will be together. And these are called as T2 and this is called as E. Okay? This is called as T2. Now you'll say, ma'am, why you have not put G over there? I'll tell you what is the meaning for G and all that. Till now, just understand, even if they have to split, right? dxy, dyz, dzx, that will be together even after splitting, and dx square minus y square and dz square will be together. It is called E and this is called T2, right? Now, ma'am, what will happen that they have to split? Okay, so what exactly will happen here, right? See, if it is a spherically symmetrical thing, like you have square planar, then what will happen? Free metal ion, they will be degenerate, right? If you have symmetrical field, then nothing will happen, right? But for example, I'll just tell you here. Now, just imagine that ligand is approaching. Okay, so I'll put again this diagram here, right, to explain you better, right? So let's see this diagram. Now guys, let's see the ligand is approaching. Okay, the ligand is approaching, right? So now when the ligand will approach, what do you think will happen? What do you think will happen? Some new girl has joined the class. There are 5 best friends, right? So they were like, wow, this new girl. They all will get very excited, right? Some new girl has joined the class. They all will get very excited, right? So 5 orbitals, they will get excited here, right? They will be like, wow, 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 I have to impress now, right? So they all will get excited. They are still best friends. They are still best friends, right? But their energy will increase, right? They are still degenerate. But now, you know what will happen here? You know what will happen here? Now, depending upon whether it's octahedral or tetrahedral, they will split. Okay. Now, after this, they will split. Right? Degeneracy will break. Degeneracy will break. Degeneracy is going to break now. But what will be here? What will be here? That is a question mark. That will be solved by taking two different examples. One is for octahedral, one is for tetrahedral. What you will fill here depends upon whether it's an octahedral field, whether it's a tetrahedral structure. The pattern of splitting depends upon the nature of crystal field, right? Pattern, how much splitting will be there? See, first thing is whether it's octahedral, right, or tetrahedral, right? Second thing is how much splitting, or you can say extent of splitting, This is what we have to learn, right? Splitting will be this much, splitting will be this much, splitting will be this much. How much splitting will be there? That will depend upon what kind of ligand you have, right? Whether it's octahedral, that will show different variations, tetrahedral, that will show different variations. So this is what we have to discuss. Firstly, we'll talk about octahedral structures, right? Okay. So let's understand the octahedral structure. Crystal field splitting in the octahedral structure. Now, who is going to tell me what is an octahedral? Who is going to tell me an octahedral? 1, 2, and 3, and 4, and 5. How many bonds? 1, 2, 3, 4, 5, and 6. Okay. So I have it here. I'll just put it here. Yes. Okay. So now, this is one bond. 180 degree, you have another bond, right? You have one bond here. It will firstly make a square planar structure, right? Right? Square planar. Now, you will have two bonds. One is above and one is below, right? Why it is called octahedral? Because it has 8 phases, right? This is the first phase, this is the second phase, third phase, and fourth phase. Similarly, 5th, 6th, 7th, and 8th. It has 8 triangular phases. That is why even after having only 6 bonds, it is called as octahedral. Means 8 phases, 8 triangular phases it will have. Right? Okay? Yes, very good. Okay. Sai, you can watch the lectures here, okay? It is the same thing, right? Don't worry about that. That's why I inform you on my Telegram channel also, Chem Catalyst Diksha also, I inform you there also, right? Okay? So, this is the octahedral complexes. Can you see that? Now, can you see if this is x-axis, this is x-axis, if this is y-axis and this is z-axis? Can you see all the bonds are along the axis? This is, let's say, y, this is, let's say, x, and this is, let's say, it is z. So, all the bonds are along the axis, right? Can you see that here, guys? Can you see that? Can you see that? Right? Now, it's the same situation, okay? So, what will happen? There will be repulsion, okay? Repulsion between, we know that there are few orbitals which are along the axis. And what are these orbitals? These orbitals are along the axis, right? These orbitals will be affected by octahedral field, right? What is happening here? You have these lobes, these d orbitals in the metal, they are along the axis, its electron density is along the axis, right? And the structure that it is going to form is also along the axis, right? So that is why it will cause the repulsion, right? And because of this repulsion, what will happen here? Dx square minus y square and dz square will have more energy, right? Because they are also along the axis, and octahedral lobes, or you can say octahedral bonds are also along the axis, and these are also along the axis, and that is the reason that here, wait a minute, these are also along the axis. This will energy will increase in octahedral. In octahedral, if you have octahedral preparation, octahedral field, then this energy is going to increase, right? Okay, understood? The same thing that is written here, as I have shown you, is the same thing, that dx square minus y square and dz square causes more repulsion, and that is the reason their energy will increase. But if you talk about between the axes, like you have dx, y, dy, z, dzx, their energy will get lowered because there is no repulsion here, right? Okay, understood? Now this is your octahedral structure that you are going to have. Firstly, in this case, there is no ligand, right? After that, what is happening? When the ligand is approaching, all of them have more energy. Energy will increase. Then after that, because some lobes are along the axis and the structure is also along the axis, so its energy will increase and T2 energy will decrease, right? Now, as I told you, this is called as T2 and this is called as E. But here in octahedral, we write G and G here. This is called as T2G and that is called as EG. Can you tell me the reason? G means gerate, okay? G means gerate. That means symmetry. That means symmetrical, right? Because this structure is quite symmetrical, right? That is why we say that here we apply G, right? Okay, understood? Now, what we'll talk about is barycenter and how much amount of energy that we are going to talk about. So if you see, this is this is T2G, this is EG. I'll just write it here as well. T2G and this is EG. Now, the energy which was the energy of degenerate orbitals when they all have rise in energy, that is called as barycenter. That is called as barycenter or barycenter. Barycenter. Now from barycenter till this EG orbital, you have plus of 3 by 5 and here you have minus of 2 by 5. Okay? Minus of 2 by 5 and plus of 3 by 5. Right? Okay, everybody, wait a minute. Yes. So 2 by 5 is nothing but it is also called as minus 0.4 and this is also called as plus 0.6. Minus of 0.4 and this is called as plus of 0.6. Right? Okay, everybody. Now, what is the benefit of this thing? First, you tell me if till here you have any problem, right? Yes. Yes, Muthu. Yes, Sai. And then we have Sai Priya, then Future Itian, Selvion, Jack. Yes, everybody. Right? Yes, everybody. Tell me. Is that clear? Is there any problem in this particular thing or not? So that I can start with the next thing, right? Okay. So this is what we have done already. Now let's approach to the next thing. That is this also we have seen that this is T2G, this is EG. Now if you talk about calculating this splitting, okay, this is nothing but this is called delta O. This is called the splitting, right? So how you will calculate that? Let's see. Energy separation is denoted by delta O. That is called as, this is actually delta O. The subscript O means that it is octahedral. It is called as crystal field splitting energy, CFSE. It is measured from strong and weak both the ligands, right? So I'll tell you what is exactly strong ligand, what is exactly weak ligand, right? Now see one thing. Two EG orbitals, it is increased by plus 3 by 5, that is plus of 0.6. And this T2G orbital is decreased by minus 0.4. This is the same thing that I have written here, minus this and this. You know how you will solve the CFSE, right? From this value itself, right? So, wait a minute. Firstly, just let me tell you. Do you want to know the CFSE first formula? Chalo. That we'll talk about. Here only I can tell you that, right? CFSE is nothing but it is number of electrons in T2G multiplied by minus of 0.4 plus number of electron in EG multiplied by 0.6. Okay. So let's say you have one electron here. So 1 multiplied by minus 0.4 and this you have 0 electrons. So 0 multiplied by 0.6. That will give you your CFSE. Right? So that is the formula. We'll also do questions based on that. Don't worry. This is a JEE 2025 question only that I'll show you. Right? Okay. Now, next thing is we have seen CFSE, but there is some dependence of CFSE as well, right? So it depends upon so many things, right? So first, it depends upon the charge on the metal ion, right? So how does it depend upon the charge? See, more is the positive charge, more will be the electrostatic interaction, and hence CFSE will be more. So if I have to see, increase with increasing charge on the metal, and that too we are talking about positive charge. See, if I have to see CFSE between, let's say, M2 positive and M3 positive, which has more CFSE. This M3 positive has more CFSE and it is increased by 50%. It is increased by 50%, right? So based on this also they ask you the questions that are based on statement based questions, and they can ask you increasing, decreasing order of CFSE. That is where we will use this thing. Okay. Now, next thing guys, let's see that. Whether the metal is first, second. Next thing is depends upon whether the metal belongs to first 3D series, 3D I'm saying, first D series, then second or third transition series, right? Or third. First is nothing but we are talking about 3D. Then we are talking about 4D. Then we are talking about 5D. Now here also from 3D to 4D, 30% increase in CFSE is observed. For the same ligand, for the same charge, you will see 30% increase in CFSE. From 4D to 5D also, you will see 30% increase in CFSE. So can you see one thing that here on increasing the charge, CFSE is increasing. On increasing the 3D series, 4D to 5D, it is increasing, right? Then, as we have written it here, it is increased by 30%, right? Now, if you talk about the different complexes that we are going to see, square planar is not in your syllabus, right? You only have octahedral and tetrahedral, but you should know which has maximum CFSE. Square planar, then octahedral, then tetrahedral, right? Octahedral definitely we are discussing, and tetrahedral also we are going to discuss. We are also going to discuss the relation between octahedral and tetrahedral. How much increment is there? That also we'll discuss, right? Okay. Then there is nature of ligand, right? What is the nature of ligand? That also defines CFSE, right? Now, nature of ligand is of two types, right? So one is a strong field ligand, one is a weak field ligand. Strong field ligand will cause very high splitting, right? Weak field ligand will cause less splitting, right? So let's see that. If you see, in weak field ligand, it causes very less splitting. That means interactions will be less. Less interactions and less repulsions. Less rise in energy of Eg and decrease in T2G. It means less crystal field splitting. Right? For a strong field ligand, the interactions is very high. That's why splitting is very high. Reason being because more attractions, more repulsions, and hence rise in energy of T2G is more. And here, earlier it was at this level. In weak field, this has slightly increased, this has slightly decreased. That's it. But in strong field, this has increased. EG has increased to this much level. This T2G has increased to this much level. Now the splitting is very high, right? So that is the concept of strong field and weak field ligand, right? Next concept is of pairing energy. Now I'll make a chart so that you can remember weak field, strong field, low spin, high spin, everything, right? So if you talk about a strong field ligand and a weak field ligand will cause no pairing. There will be no pairing. This we have discussed in BBT also, right? And this will cause pairing. Now, as I told you in VBT also, that what is the reason that strong field is causing pairing and weak field is not causing any pairing? There must be some reason based on which we are saying this thing, right? So the reason is that in low spin, firstly, what is a low spin complex? Where pairing has happened, right? Where pairing has happened. Let's say you have 3 electrons and all of them are paired up, right? Let's say you have 6 electrons, all of them are paired up. So the spin is less because all are cancelling each other. But if you talk about here, you have 6 electrons, 1, 2, 3, 4, 5 and then 6. Now what you will see, there is unpaired electron, that means it is high spin, okay? That is the concept of low spin and high spin, okay? So this is pairing and here you will have no pairing, right? That means, can I say this is strong field, this is strong field and this is weak field, this is weak field, okay? Now here, when pairing it has caused, see, tell me one thing, you want to purchase one, let's say you want to purchase, what you want to purchase, right? What do you want to purchase? Let's say you want to purchase shoes, right? Now you have gone to 2-3 shops, right? Same quality of shoes you're getting at 700 rupees, same quality of shoes you're getting for 1000 rupees. You will definitely purchase 700 rupees shoes, right? Because that is causing you less money, right? So now same thing is happening here. Let's say you have pairing energy and delta O, this is CFSE. CFSE is causing you, let's say 1000 rupees. This is causing you 700 rupees. Still go for the one which is causing you less money. So that's why pairing is chosen here, because pairing needs less energy as compared to CFSE. CFSE, the crystal field splitting energy is high. So the electrons are like, if I have to split this, the ligand is like, if I have to split this, I'll have to give more energy. If I cause the pairing, I'll have to give less energy. So it goes for pairing, right? So that's why P is less than delta. But in this case, this is causing you 1000 rupees, this is causing you 700. So definitely you will go for delta O. And that's why in strong field ligand, there is no, that's why in weak field ligand, there is no pairing. Yes. So in weak field ligand, there is no pairing, right? Because pairing needs more energy here, right? Okay, right, everybody? Here the CFSE gap will be very high, right? The gap will be extremely high, and here the CFSE gap will be very less. Okay, so that is the full-fledged concept which you have to remember if you want to do the questions, where they can say low spin, they can say pairing, they can say strong field, they can write this, they can say CFSC is very high. This all means the same thing, right? They all means the same thing. They can just confuse you by writing different things there, right? Okay. Ajay, that is find out experimentally, right? Experimentally, it was find out that pairing energy is less. And that is the reason it wants to do pairing energy. It wants to do pairing because less money is needed. Right? Okay, is there any problem in this particular concept, students? Do let me know. Yes. Now, what is the benefit of this theory? It gave you proper spectrochemical series, right? It gave you this series of less, less strength ligands, weak field ligand to strong field ligand, increasing order. That is called spectrochemical series. So from weak field to strong field, it has given us all the ligands, right? So you have to learn this because based on this also they ask you the questions directly. In JEE Mains, they ask you direct questions. In JEE Advanced, definitely the questions will be mixed level, right? Okay. So, okay, yes. Now, for this, I have made a trick for you guys, right? So I broke Samantha's clock. She found out, called Harsha. Nobody ever noticed any cracked clock. So you can make your own mnemonic, you can make a song, anything, whatever you like, right? So do whatever you like, right? You can make a mnemonic in your own language, in your regional language, in English, in mixed languages, totally your choice. In the end, you just have to learn this series, right? For this, I have already shown you I broke, IBr, then SCN, then Cl, then S negative, Fn, F negative OH, then oxalate, then H2O, NCS, ETTA, NH3, EN, CN, and Cu. Okay? Yes, everybody? Right, students? Tell me, everybody. Okay? Yes. Now, let's do the next thing. Strong field ligand leads to absorption of light, more energy, smaller wavelength. What do you mean by that, ma'am? See, we know that E is equals to H mu. That is nothing but Hc by lambda. So I can say energy is directly proportional to mu, inversely proportional to lambda. Right? So, what is happening here? When you have a strong field ligand, it is causing very high energy splitting. So, if energy is very high, that means lambda will be very less. The light that it is absorbing will be very less. Leads to absorption of light, more energy, and less wavelength, because wavelength and energy are inversely proportional. Weak field ligand leads to absorption of light with less energy because the splitting is very less. So they have taken C. Simple thing is ligand is also like absorbing some light from somewhere, right? So when it is absorbing the light, and that is the reason it will give rise to colors also. We'll talk about that. But for now, just understand one thing, where it is absorbing the light, right? It is absorbing the light. Now, when it is absorbing the light, it is going to give rise to some lambda also, some lambda, that energy will have some lambda. So if splitting is very high, that means the energy absorbed is very high, lambda is very less. If splitting is very less, then energy absorbed is very less and the lambda is very high. This is what is written here, right? Now, students, one by one, we are going to talk about the electrons here. Okay. Yes, everybody. Better don't worry, that's our duty, okay? Don't worry. That's why we have multiple teachers for you in the Sigma batch. Huh. Beta, I am not speaking very difficultly. I am taking in speaking, right? So, if you don't respond, then I'll also go on that pace only. Okay, now my throat is actually having some problems. Hmm. Right? Okay. Now D1, D2, high spin, low spin, everything we'll talk about, right? So for D1 high spin complex, high spin means what? Pairing or no pairing. I have taught you here. High spin means there will be pairing or no pairing. This is high spin. High spin means strong. HS, HS, HS. High spin strong. High spin. Low spin weak. LW, LW. Okay. High spin is strong. Strong field will cause the pairing. Here you have D1, so here it will be 1, 1 and 1 electron here. If you have low spin, that means weak field. If here you have 1, here you have again, here you will have 1. Okay. D2, high spin means strong. Here you have 1, 2, 1, 2. Here these three are degenerate. So it will say 1, 2. Okay. Even for low spin, it will have the same situation. Even for weak, it will have the same situation. Okay. Yes. Because even if you're saying, ma'am, the second electron is not getting paired, pairing will not happen like that, right? Here, pairing will happen. Firstly, same degenerate orbitals will get filled. Firstly, you will have fill all these three orbitals, right? Then we'll think about pairing or no pairing. D3 strong is 1, 2, 3, 1, 2, 3. And here also it is 1, 2, and 3. Right? Next is here what you have. This is D3 low spin, that means weak. This is 1, 2, 3. Same thing. Because firstly, degenerate orbitals are singly filled. Then we will think about pairing. Now, this is important. Strong field. Right? 1, 2, 3, 4. Right? Here also 1, 2, 3, 4. Here what will happen? It will cause pairing. So it is 1, 2, 3. Now fourth electron, either it can go here or it can go here. Because the gap is very high. So it will go here. Right? It will move here. Right? Okay. Next is low spin complex. Low spin complexes, students, it means weak. It is 1, 2, 3, 4, 1, 2, 3, 4, and this will be 1, 2, 3 because it's a low spin complex. This gap is less. So what will happen? Fourth electron will jump here. Can you see this change here? Here you have 4 electrons and here you have 0 electron. Here you have 3 electrons and here you have 1 electron. Can you see this change in D5 also? It is same. Strong field. 1, 2, 3. Fourth will be here. Fifth will be here. Right? Okay. If you talk about weak field in D5, 1, 2, 3, 4, 5. In here, what will happen? 1, 2, 3, 4, and 5, because the gap is very less. Okay, the gap is less. Next is D6. Again, strong. 1, 2, 3, 4, 5, and 6. Here you will write it like this. Right? Now, here 6 electrons, how it will be filled. 1, 2, 3, 4, 5, and 6. Because it's a strong field, pairing will happen. Right? Here it is weak. So 1, 2, 3. This is so beta simple, how you used to fill in before also. Now here you will do 1, 2, 3, 4, 5, and then 6. That's how you're going to fill the electrons, because the gap is very less. Pairing will not happen. Pairing will happen once all the orbitals are filled. The gap is less, the electrons can jump here, right? Because they require less energy to jump. D7 high complexes, strong, and this is 1, 2, 3, 4, 5, 6, 7. Right, this is the same thing. Now I'm not going to fill these two. Okay, I'm just focusing on this one. Right, this you can do yourself. Okay, I'm going to just fill this. Okay, 1, 2, 3. Strong fill means pairing will happen. 4, 5, 6, and then 7. Right, here it will be for weak ligand. 1, 2, 3. Then 4, then 5, then 6, then 7. Can you see one thing? This is the same diagram. No. This is not the same diagram. This is for D8, you will have the same diagram. This is strong field. Pairing will happen 1, 2, 3, 4, 5, 6, 7, 8. Right? For weak field, see, the way I am filling the electron will be different, but result will be same. 1, 2, 3, 4, 5. Now I will fill these two firstly. Then 6, 7, 8. Can you see one thing? Strong and weak is giving us the same result. Way is different. Here firstly I filled 1, 2, 3, then 4, 5, 6, then 7, 8. Here I filled 1, 2, 3, 4, 5, 6, 7, 8. Result is same. Similarly for D9, strong and weak, I am drawing it. So strong I will draw here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Weak field, how you will draw it? 1, 2, 3, 4, 5, 6, 7, 8, 9. Isn't it the same diagram? Same diagram. Right, everybody? Let's do this. Strong field, it's definitely same, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And for weak field, 1, 2, 3, 4, 5, 6, 7, 7, 8, 9, 10. Got it, everybody? Tell me, if you have any problem in filling the d orbitals, right, in octahedral field in low and high spin. And here you can observe one very important thing, that for, wait a minute, where it was, yes, for D1 it is same, right? Wait a minute, sorry. For D1 it is same, for weak and strong. For D2 it is same, for D3 it is same. For D4, D1, D2, D3 it is same, right? Then you talk about D8. There is D8. Here you have D8. See, D8 strong and weak, it is same. D9 strong and weak, it is same. D10 strong and weak, it is same. So I'll just write one thing here that you must know. I'm going to write it here, right? Okay, let's write it here that D1, D2, D3, D8, D9, D10. For these cases, for these cases, what you will just simply say, weak and strong field in octahedral. In octahedral have the same electron in T2G and EG. Right, this is a very, very important thing. This will save you a lot of time. Okay? Right, everybody? Okay, sure. Now, this is the formula that I gave you before also. Number of electrons in T2G multiplied by minus 0.4 plus number of electrons in EG multiplied by 0.6. Okay, number of electrons in EG, number of electrons in T2G. Okay, so we are going to fill it. Let's see JEE Mains 2025 question. Let's solve this. Okay, you will get an idea how questions are asked. Right? Ready to solve it with me, everybody? Ready? Ready? Sai, please focus here now, please. That's a request. Please focus here. Okay? Shall we start, guys? Tell me. Shall we start solving? Achha. Let's do this. Here, what you have, the d orbitals of electronic configuration of the complexes among this that has highest CFSE. Highest CFSE. Okay, so one by one we'll solve it. Right? Firstly, what I'll do, I'll solve the electronic configuration. Right? Firstly, I'll solve the electronic configuration of all of them. Let's take COEN thrice, COEN thrice, 3 positive. That is nothing but X is equals to plus 3 because this is a neutral ligand. So cobalt will be plus 3. See, cobalt is nothing but 4s2 3d7. So cobalt 3 positive will be nothing but 3d6. Beta, En is the strong field ligand, right? If you see this, wait a minute, this series here, En is among the strong field ligand, right? So can I just solve this by saying that En is a strong field ligand? So here what I'll write, this is 1, 2, 1, 2, 3. So En is a strong field ligand. It will be, this is T2G, this is EG. So this will be, electrons will be 1, 2. You know what I'll do? Chala, let's do this only. Right? 1, 2, 3. Because it's a strong field ligand, it will cause the pairing 4, 4, 5, 6. Okay? Okay. So electronic configuration you can write T2G 6 and you have EG 0. Okay? Then you have COF6 3 negative. COF6 3 negative. Again it is going to have X is equals to 3. X minus 6. X is equals to 3. So cobalt plus 3 is nothing but 3d6. 3d6. Now, this was a strong field ligand. This was a strong field ligand. But F negative is a weak ligand. It's among halides, weak field. Here, 1, 2, 1, 2, 3, because they all are octahedral. 6 and En3, but En is bidentate ligand, so it will have 6 donating sites, so it is also octahedral, right? Usually questions are asked based on octahedral only. So weak means 1, 2, 3, 4, 5 and 6. Now you can see it will be T2G4 and EG2, right? Let's discuss the third one here. MnH2, 6 and 2 positive. MnH2O, 6 and 2 positive. So Mn is nothing but 4s2, 3d5. Mn2 positive will be nothing but it will be 3d5. Okay, it will be, you take out 2 electrons. This I have already taught you in D block also, and I have taught you before also, right? Now H2 is a weak ligand. Okay, it's a weak ligand. It's a weak ligand. Here it will cause splitting like 1, 2, 3, 4, 5. And here it will be T2G3 and EG2. Last one is you have ZnH2, 6, 2 positive. ZnH2, 6, 2. Zinc is nothing, it is 4s2, 3d10. See, water is a neutral ligand, so it will be X plus 0 equals to plus 2 is plus 2, zinc plus 2. So zinc plus 2 is nothing but you take out 2 electrons here, it will be 3d10. See, it doesn't matter in 3d10, you have weak field or strong field, right? But still, we know that this is a weak field ligand, okay? Halaki, it doesn't matter, but still we know this. 5, 6, 7, 8, 9 and 10. Right? Now, now you have all the electronic configurations here, right? Now you need to tell me, they are asking you that which will have highest CFSE. Okay, so you'll have to write it. So you know what I'll do? I'll just pick out this thing here, right? And I'll solve. I'll erase everything else and I'll just solve this value of CFSE. Okay? Okay, because what we needed was electronic configuration that we have. Now, number of electrons, this is minus 0.4 multiplied by 6 plus 0. That is going to be minus 6 4 24 minus 2.4. This will be minus 0.4 multiplied by 4 plus 2 into 0.6. That is 4, 4, 16, 1.6. This is 6, 2, 12, 1.2. So it will be 0.4. Right? Here it is minus 0.4 into 3. I hope so I don't do any calculation mistake. Right? 2 multiplied by 0.6. See, T2G is multiplied by minus 0.4 and EG is multiplied by 0.6. 4, 3, 12 and this is 6, 2, 12. So it will cancel out. This will be 0. I think this will be the answer. Let's see. Here what you have, minus 0.4 into 6 plus 0.4 into 4. 6, 4, 24 and this is 4, 4, 16 and here definitely it is going to be in minus, right? So out of this, the value that is coming out to be maximum is 0.4, that is for COF6, right? And that is what? Maximum Maximum or minimum they are asking you? Configuration which has highest CFSE. Highest CFSE. Hmm. Either the answer is marked wrong or I have done any calculation mistake. I don't think so I have done. 6424, this definitely cannot be the highest. If EG is 0, that cannot be highest. You have to have EG somewhere, right? Answer will be T2G 4EG2. Okay? Answer will be this, not this. Okay? So, answer will be this one. Okay? Because that is highest CFSE is not possible there. Right? Okay? Okay, success. I'll put that. Okay, we'll start with the PYQ series. Okay, one day we'll do PYQ of one of the chapters. Okay, I'm just waiting for to complete at least coordination chemistry so that we can start with PYQs and solve JEE advanced questions as well. Right? Okay. Yes, everybody. So after this, let's talk about tetrahedral complexes. Right? Let's talk about tetrahedral complexes and let me see how many likes. Very few. Yes, Naseen, I am looking at your live chat. Uh, Low spin means pairing. Yes, different way. Can you go and check it where you gave that low spin means pairing and strong field? I didn't get your question. Yes, low spin means pairing only, and high spin means no pairing, right? So let's talk about tetrahedral angles. Okay. So in tetrahedral, just okay, it's not that of a okay. Chalo. Now, I'll write something here which is important for you to know, right? See, in tetrahedral complexes, firstly, you should know the structure of tetrahedral, right? So, I'll just draw the structure of tetrahedral, right? Now, same way we will see whether it is along the axis, between the axis. But for tetrahedral, no, it's a very interesting thing that they can ask you in theory based questions, right? Okay. So if you see this here, in tetrahedral field, it's not like this is, if you see this is along the axis and this might be between the axis. But it's not like all the bonds are along the axis or between the axis. There is no exact thing here, right? So that is the reason, right? That is the reason here. Here we said that those will be affected which are along the axis. But here if you see in EG and T2G, here the angle was 54 degrees something, I think 44 minutes something was there. It was 35 degrees something was there. Let me see the exact value here, right? 35 degrees 16 minutes and this was 44. So this was 44 minutes and this is 16 minutes. How we got this? Don't get into that much maths, okay? So simple thing is here you have this much angle, here you have this much angle. Where the angle is less, that will be affected. So the angle between ligands and T2G is this much. Here EG and the ligand is this much. So we can say this is less angle, so more affected. So energy will increase, right? If you see this here, here you have more angle, so it is less affected, right? That is why in case of tetrahedral, you have T2G is having more energy as compared to EG. But here along the axis, that means EG was affected. Okay, so EG energy was more, right? So that is the reason tetrahedral and octahedral has entirely different, but the reason is different. Here angle and ligands are here d orbitals were along the axis, these, right, and the octahedral structure is also along the axis, right? So that's why EG was increased. But in this case, things are different. And here we don't use G. Here we simply write this is E and this is T2. Because there is no symmetry in tetrahedral. Right? So that is why we don't write G here. We don't write gerate here. Right? Okay? Low spin means, beta, with that is right, na? Low spin means, beta, low spin means there will be pairing. That's why it will have low spin. So low spin means strong field. Na? That's why it will have pairing. Right? Strong field means it will have pairing. Pairing means the spin will be less because pairing has happened. Right? Okay. Now let's see this here. What is the difference? It will be exactly opposite. Here from T2 to berry center, this is 0.4 and here it is minus 0.6. So that's why when you calculate the CFSE here, it will be 0.4 multiplied by electrons in T2 plus minus 0.6 multiplied by electron in E. Okay, that is the answer for this one, right? And very interesting thing here is, firstly, for tetrahedral orbital splitting, axial are named as T2, and this there is no gerate, G is not used because there is no center of symmetry, right? In tetrahedral entity formation, the d orbital splitting is smaller. It's a very, very important thing. So in tetrahedral splitting, it is always, there is no concept of high spin, low spin, right? Tetrahedral splitting, if it is happening, it is always going to follow weak field. It is always going to be high spin. It is always going to be high spin, right? It is always going to be high spin, right? So delta O is always greater than delta T. Now this formula we write, but I'll tell you how we write this formula, right? So why delta O is always greater, ma'am? Why delta T is always less? Any idea on this? Any idea? See, delta O is always more. First reason is, in delta O you have 6 ligands and in tetrahedral you have 4 ligands. So that's why delta O is more than delta T, right? Acha, tell me one thing. It is how much more? It has 4 ligands. It is having 6 ligands, right? So if you see this here, 2 by 3 into 6, that is nothing but 4. So can I say because of this reason, delta T is nothing. If this is delta O, it is 2 by 3 because of this reason, right? If it is having six ligands, so then it will have 4. We know that octahedral has 6 ligands, this will have 4 ligands. That's how this particular thing was formed. Okay, this is not the exact formula. I'm just telling you how from ligands this quantity was derived. And then we know that the direction of orbital does not coincide with the direction of ligand. In octahedral splitting, it was overlapping. Direction of ligand and the direction of the orbitals both were along the axis. It was coinciding, it was overlapping. That's why large splitting was also observed. But in tetrahedral, there is no concept of overlapping. It is because of the angle. Not even in along the axis, not in between the axis, it is exactly overlapping. It's because in between the axis, angle is less, so we have taken that, right? So there is no coinciding as such. And that factor will give us 2 by 3. Okay, so we can say combining this and this, these two reasons, we have delta T, very, very important. 4 by 9, you multiply 2 by 3 multiplied by 2 by 3, 4 by 9, this is delta. So 2 by 3, we have picked it out from these two reasons. Okay. Low spin act as weak field. Have I? Wait a minute. Let me just see. Oh, yes. I'll just correct that. Low spin means strong field. Acha. Wait a minute. Low spin, strong field. Have I written that only? Oh, yes, beta. So sorry. Yes, Nisan, you are right. High spin. Acha, by mistake, I have written here. But I have taken all the terms wrong, है ना? Okay. So high spin nahi. Do I have to write it again? Okay. High spin is weak field, right? Low spin is strong field. High spin is weak. Okay, beta, correct it. Low spin is strong. High spin weak. Low spin strong. Right? Strong. Here things will change. High spin weak. So weak will have this 1, 2, 3, 4. And here it will be strong. Just give me a second. Let me just correct all of that. Low spin is strong. So it will be 1, 2, 3, and 4. Right? Oof. High spin weak. Again, it will change 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5. Spin strong. You know what I'll do? I'll just erase this. Okay? Better. I'll just erase high spin and low spin. This is low spin. Means strong. This is high spin. Means weak. Okay? So I'll just change this only. This is low spin. This is high spin. low, high, low, oof, high. Okay, low, high. Finally corrected. Okay, thank you for correcting, Nissan. Thank you. Okay, chal. Now let's solve these few points we are going to cover. First is why tetrahedral complexes are less stable, right? Students, why tetrahedral complexes are less stable? Anybody, anybody? Yes, everybody. Why tetrahedral complexes are less stable? Yes, students, why tetrahedral complexes are less stable? First point is same because delta O that we have measured there, that is 4 by 9 of, sorry, delta T is 4 by 9 of delta O. So because delta T is less than delta O, so that's why firstly it is more stable. Octahedral complexes are more stable and tetrahedral are less stable, right? Second is you have 4 ligands. It is the same thing only. 4 ligands in tetrahedral, right? Which corresponds to less energy. Less energy as compared to 6 ligands. See, if you have 6 ligands, that means 6 bonds are formed. That means more energy will be released. More energy will be released. Hence, octahedral complexes are more stable. Hence, octahedral complexes are more stable. Okay? Yes. Next is tetrahedral complexes are favored in what cases? In some cases, tetrahedral will be favored. First is, let's say ligand is very heavy. Ligand is very heavy, very large. Because of that, if the ligands are very large, it will cause repulsion, right? It's the same thing that why certain they exist in L6 and why certain have four ligands only. Why some complexes exist in tetrahedral? Because ligands might be very heavy. That can be the first reason. Because to avoid repulsion, if ligand is very heavy, so repulsion will be there. To avoid it, to avoid repulsions, they are in the tetrahedral. Tetrahedral, they adapt the tetrahedral structure, right? Because of these repulsions, they adapt the tetrahedral structure, right? Then, second is D0, D2, D5, and D7 and D10. I'll tell you why these are very stable, right? So if you talk about tetrahedral complexes, right, you have 2, then 3, 2, then 3, 2, then 3. Okay, I'll tell you why I'm drawing this. 2, 1, 2, 3, 2, 1, 2, 3. Okay, have a gap between all of them. 1, 2, 3, and 4. If you see, you make D0, it is more stable in tetrahedral. If you talk about D2, it will have 2 electron. It is having a symmetrical thing. 1, 2, 3, 4, 5 in D5 also in D7. 1, 2, 3, 4, 5, 6, 7. Again, it is more stable. Or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can you see in all these complexes, in tetrahedral, you have a symmetry, right? So if you are in D0, D2, D5, D7, D10 configuration, okay? Okay? Then third will be central metal atom is in lower oxidation state. Central metal atom is in lower oxidation state. And fourth is you have weak field ligand. So then it will prefer the tetrahedral. Prefer, I am saying, weak field ligand. If you have, it will also prefer tetrahedral. Okay. Now, question of JEE 2024 is the number of complexes from the following with no electrons in T2 orbital is. Okay. No electron in T2 that you have to solve. Okay, everybody, beta, what? I don't know what you want. So less, I mean, very few students who are actually here. Ma'am will, kill her throat for you, but you guys will not respond. Chalo. Number of complexes from the following with no electrons in T2. Beta, I need some rest. My throat is literally not well. Solve this. I think you can do this yourself also. No T2 electrons you have to find out. First is x minus 4 is equals to 0, x is equals to plus 4. Titanium is T, so it is 22, it is 4s2, 3d2. You take out 4 electrons, it will be 3d0. So definitely T2G will have 0 electrons. Right. Next is MnO4 negative. It will be x minus 8 is equals to minus 1, x is equals to plus 7. Mn is nothing but, you take out 7 electron, it will be D0. That means T2G will have 0 electron. Okay. So first two definitely have 0 T2G electron. Here FeO4O negative. Okay. Okay. Three D0, right? Now in this what you will have? Again, T2G is going to be 0. 6 electrons, no? So it will be 3D2. And here it is a tetrahedral field, right? So it will be 3 here, 2 here. So definitely T2G is 0. Right? Next is, this is also 0, FeCl4 negative. But I am speaking slowly because my throat is not well. Okay. 3d6. 2 plus 1 you take out, 3d5. It will have, see, 4 means it will be tetrahedral like this. T2G will be raised. 1, 2, 3, 4, 5. So T2G has 6 electrons. Okay. Last one. Let's see this here. Okay. COCl4. I'll just do this here. This does not have. X minus 4 is equals to minus 2, x is equals to plus 2. Cobalt is 4s2, 3d7. Cobalt 2 positive is 3d7. It will also have. Okay, how? It is tetrahedral, no? So it will be 1, 2, 3, 4, 5, 6, 7. So again, T2G, or you can just simply say TG. T2. You will write instead of this, you will write T2 here, not G. G you will not put only, na? So it will be T2. It will be T2. It will be T2. It will be T2. So 3 have T2G is equals to 0 electrons. Okay. Yes. Beta, I have raised the concern with the team. Don't worry. Okay, that is getting sorted. Now, next is color of coordination complexes. If you see, color is observed because of 3 things. Okay. That we have discussed in D block. Because of DD transitions, right? Because of charge transfer, we discussed about MnO4, 2 negative K2MnO4, KMnO4, KMnO4 negative K2Cr2O7. So Cr2O7, 2 negative, right? Then it has LMCT, MMCT, right? Different kind of charge transfer, right? Then there is polarization. Because of which AgBr, AgI, they have the colors, right? Now, in this chapter, we are going to focus on this thing, right? We are going to focus on DD transitions. Like we discussed in DNF block that because of DD transition, color is there. But why? Why color is there? Because of DD transition, right? This is because of charge spectra. Like they both don't show color because of DD transition, but because of charge spectra, right? Now let's talk about what is this DD transition. Okay, let's understand that. Any example you can take octahedral, tetrahedral, totally your choice. I'll take octahedral. Okay, so octahedral is 2, 3. This is EG. This is T2G. Okay. Some electron is over here, right? Now take it as your home. You're in your home. It's not like you always want to be in your home, na? Right? IIT in Bombay, I'm going to take that only on Friday, right? See this now. You have 1 electron. Let's imagine you are in your home, right? So tell me one thing. When you are in your home, it's not like you always want to be in your home, right? No, right? It will be a home jail, right? Similarly, electron also is same like that. Electron is happy in the home, but it's not like it always wants to be in the home, right? If it will get some energy, oh my god, I want to go to school also to meet my friends. I want to go to coaching also to meet my friends. I want to attend this particular session because I want to talk to my friends, right? I want to like go with my friends on in some party. I want to, see this mall. I want to go to shopping. We all humans, we need this, right? So similarly, this electron also will absorb some energy. It will also get excited, right? Now, electron is absorbing some amount of energy. It depends upon different things. It is getting excited. Now it's not like you want to go to this mall, right? You want to watch the movie and you are sitting on in the theater. You love Ciara movie. You are like, oh my god, everyone is fan of this Ciara movie. I'm gonna go there and watch it. And till the theater end, you are there only, looking at Sayara. No, it's not like you're sleeping there. Then you're like, okay, this theater is my home. I love this movie. Day and night, I want to watch this. No, right? You feel like, yeah, I want to go home, right? Every time you want to feel like, I want to go home. Similarly, this electron is happy in its ground state only. So it will also go back to his home, right? Or you can just draw it like this. It will go back, whichever, it's not like it will go to this particular orbital. It can also stay here. It can also stay here. It can also stay here, right? I'll put here. Now, this we talked about that electron will absorb some energy, and corresponding to that energy, it will emit some energy. Here it is going to absorb the energy. Here it is going to emit the energy. And these are called as DD transitions. Because of this DD transitions only, it gives us some color. Because when it absorbs energy, right, that will have some lambda, that will have some energy, right? Complementary to that, it will emit some energy. And this energy will have some, like lambda, will have some energy, it will have some color, right? And this is the color that we see, right? So this all thing is written here, what I told you, right? Now let's see the wheel. Okay, let's see the wheel. Right, everybody? Okay, if you see the wheel, right, you might get confused, right? So I'm drawing it simple for you, right? I'm going to just draw 3-4 lines here, right? Let's say first line is this one, then you have this line, then you have, let's not draw it like this, okay, then you have this line, and then you have this line. Okay, simple 3 things you have to learn: V, Y, okay, O, B, right, and then you have R, G, R, then G. Okay, just remember this thing. Okay, same timing, it will be at 6 p.m. Tomorrow also I have coordination compound class, which is for isomerism. After, see, Wednesday and Thursday is for class 12, and Friday and Saturday is for class 11. Okay, now tell me one thing: VY RGOB, if it is absorbing violet color, it will give you yellow color. If it is absorbing orange color, it will give you blue color. If it is absorbing red, it will give you green color. Opposite, if it is absorbing yellow, it will give you violet. Blue, it will give you orange. Green, it will give you red. Right? So that is called the wheel. Okay? So based on this field, you will see yellow is giving violet, blue, green is giving red, blue is giving us yellowish, orange, ultraviolet, pale yellow, red, blue, blue, green, violet. So approximately this thing, right? Next, and this now you can learn because this is like important thing, important chart, right? That is a factual based chart. Now we know that energy is inversely proportional to lambda. So more is the energy, lambda will be less. Same thing it is written here, right? That if energy is low, lambda will be high, that is called for longer wavelength. Energy is high, lambda will be less, that will be for shorter wavelength, right? So energy depends upon the ligand strength. So we can say this directly that ligand strength is inversely proportional to 1 by lambda, right? Okay. Ligand strength is directly proportional to 1 by lambda. If you have a strong field ligand, CFSE will be very high. So lambda will be very less. If you have a weak field ligand, CFSE will be very less. Lambda will be very high. Okay. Yes, students. So now do this question for from JEE 2025. Right. Let's see this question. The correct order of the complexes. These complexes are given to you. D in terms of wavelength of light absorbed. Right. Wavelength of light absorbed, that is inversely proportional. If you see this here, there are so many factors that are dependent. CFSE is inversely proportional to lambda. CFSE depends upon the, firstly it depends upon the 3D, 4D, 5D series. So all the elements are same, that is cobalt. Okay, good. Now it depends upon the metal ion. More is the positive charge, more is the CFSE. Here it is CO3 positive. Here it will be CO3 positive, right? Here it is CO3 positive. Here it is x minus 1 is equals to plus 2. Again it is CO3. That means based on charge also we can't tell anything. Based on 3D, 4D we can't say anything. Based on ligand we can say, right? CN is a very strong ligand, right? All of them are octahedral also, so based on that also we can't say anything, right? One thing is strong and weak field. So this is the strong field ligand. So it will have highest CFSE. So C will have highest CFSE. If I talk about CFSE, lambda will be least. So lambda will be least, so answer will be C. Okay, still we'll talk about other things. NH3 is poor as compared to that. After this, you'll have NH3, that is B. Then you will have NH3 with water, because here the differentiating factor is water and Cl. Out of this, water is little bit stronger as compared to Cl. Okay, so Cl will be least and this will be A. Opposite order is for lambda, CBAD. CBAD. C is the correct answer. Okay, understood? So you have to take care of all the possibilities that I gave you. Firstly, I thought about metal oxidation state. Then I thought about 3D, 4D series, 5D series. Then I thought about tetrahedral, octahedral. Then I thought about strong field ligand. Okay. Yes. See this. When ethane 1,2 diamine, this is actually a factual based question. 1,2 diamine progressively added to aqueous solution of nickel chloride. The sequence of color changes observed is JEE 2025 question. Okay. So ethane 1,2 diamine. is added to nickel chloride. So there is a compound. This is actually a question from your NCRT itself, and it's a very important question. It's a factual question. Okay. So this firstly is going to give you, when it reacts with En, it is going to give pale blue color. Then after that, pale blue color will further react with En. Progressively, they are saying, they will give bluish purple color. Then it will further react to give violet color. So you can say the answer will be green firstly, because firstly it is of green color. Green, pale blue, blue, and then violet. So answer will be D is the correct answer. Okay. Next is, when I started the session, I talked about that ruby and emerald, right? How they get their colors. Okay, so let's talk about that. So when you talk about ruby, right, it actually has this formula, aluminium oxide. Okay, so what exactly happens here? In the position, on the position of El, it is replaced by Cr3 positive. And if you see Cr3 positive, Cr is nothing but 4s1 3d5. Cr3 positive is 3d3. And that is the reason it will show you transitions here. Right? It will show you transitions here. Right? Because of this reason, you will see the transitions of 1, 2, 3 going here and there. Right? DD transitions will be observed here. And because of that, absorption and emission color is observed. So continuous DD transition, it gives us red color. Right? Though it is just 0.5 to 1% of it is replaced by Cr3 positive, but still it gives us color. Then there is this emerald that you must have seen. Celebrities wearing it. So this emerald, okay, this is emerald, okay. Cr3 positive ions occupy octahedral sites in mineral beryl. So actually there is a mineral beryl which has this formula where it occupies the octahedral sites. Again it is D3, and that is why it will show you DD transition. Okay? Understood? Yes, everybody, that is the reason. I told you that similarly all the colors we observe are the reason. Okay? Then limitations. This theory takes assumptions that ligands are point charges. As I told you before, point charges. It is ignoring that it is having some covalent character also. Follows ionic ligand should exert greater splitting, but anionic ligands actually are found at the lowest end. So it's a very interesting point. So according to this theory, a negative ligand will approach the metal more easily because it's a negative ligand, right? It's electrostatic interactions. But if you see the spectrochemical series, yes. Can you see this is a neutral ligand which is highest? These are the negative ligands which are on the lower side of the series. So it is definitely against its own spectrochemical series. That is the limitation. Then you have, it does not take account for the covalent. It's totally, it has ignored the covalent character. It's saying it's ionic character, that's it. So these are the three limitations of CFT. Further, we also have other theories, but they are not in your syllabus. Okay? Right? You only have till CFS. Now, bacha, there is a very small topic of metal carbonyls, right? Very small topic. Tell me if you want to do this. A very, very small topic of metal carbonyls we have, right? So, metal carbonyls talk about when metal they have bond with a ligand that is carbon. Okay, so this is metal and this is carbon. Now see one thing, guys. What exactly happens here? If you say, okay, so I'll draw this diagram. From this diagram, let's understand. This is the metal. Metal obviously wants to get electrons. Ligand want to donate the electron. Okay, I'll draw this simple diagram here. This is metal, this is ligand. See, metal has this work of accepting the electrons. Ligand wants to donate the electrons. So they will do so. Ligand will donate the electrons by sigma bonding. It will do so. But now what will happen, that metal also has some electrons. See, some metal have D1, some metal have D2, some metal have D3, some metal have D4, some metal have D5. They have some electron in D orbital. So that is the reason, because of these electrons in D, they will also give back the electrons via pi star bonding to the ligand. And this kind of bonding is called back bonding, or it has another name, that is synergic bonding. Synergic bonding. Do you know why it is called as synergic bonding? Synergic means give and take, right? If you're giving something to me, you'll have to take something, right? It's not like, we are just like, it's like the way you go to shopkeeper. You give them the money, you take the thing that you want to have, right? That is synergic bonding. Okay, so if it is accepting electron, it will be like, you are giving me electrons, I'll also give back electrons to you. This metal is not behaving cleverly, it is also giving the electrons back. So I'll show you this with the help of this particular thing, this diagram. This is how this is shown in carbonyl ligands. Okay, it is actually, firstly, this carbonyl has electrons that it is giving to the vacant orbitals via sigma bonding. Then metal also has some electron that it is giving back with the help of pi bond in the pi star anti-bonding orbital. I'll show you, ma'am, what is this pi star anti-bonding. Let's see this. You don't have to learn this first. You don't have to learn this. Just see what I'm telling you, okay? Just give me a second. God. 2 hours of, I think, isomerism. I'll need 2 classes to complete isomerism. Continuous 1 hour was okay, but 2 hours is literally taking a load on me. Okay, you don't have to look into this filling and everything. Just see one thing, because for coordination compound, this theory, this MOT theory is not in your syllabus. It is there, but it's not in your syllabus. Okay, just see this thing. This is the LUMO pi star, where this is the LUMO pi star orbital, where you are donating, the metal is donating. And this is the HOMO orbital, where this ligand is donating to metal. That's why, because this is donating from sigma, so it is sigma bond, because it is taking 2 pi star, because this metal to ligand, it is happening in pi star. That's why it's a anti-bonding orbital. That's why it's a pi star bond. Okay, this is not in your syllabus. Don't worry, I just showed you that why it is a pi star. This is not at all in your syllabus. Just understand that why it is pi star, because here it is accepting, and here, from here, it is donating, and here it is accepting. This is the structure of ligand, CO. Okay? Clear, everybody? This is the structure of CO, right? Now, that was about synergic bonding. Now, two important things I'm going to tell you about synergic bonding. See, if metal to carbon bond strength is very high, then carbon to oxygen bond strength will be low. Right? This will be high in which case? When metal has positive charge. For example, M2 positive, then M positive, then M negative, then M2 negative. This M2 positive will have maximum position in the position in which MC bond will be larger, right? So more the positive charge, more is the MC bond, less will be the CO bond. Tell me guys if that is clear. Okay? Yes, everybody, let me see. I hope so I have not forgotten anything. I'm just going to write an example for you. Oh, I have written opposite of this. Wait a minute. Wait a minute. I have written opposite. Wait a minute. See, MC bond strength will be more. MC bond strength will be more if metal has more electron density. If metal has more electron density, so more synergic bonding it will have. Understood now? If metal has more negative charge, more electron density, it will give rise to, it will show back bonding more. More is the back bonding, more is MC bond strength. If this is bond strength is more, this bond strength will be less. Okay? Yes, everybody. Now I'm going to write one example here. Right? MnCO6 positive NiCO4. So I'm going to write one example here, right? Mn, just give me a second. This example is MnCO 6 positive. Then you have NiCO4. Then you have CrCO6. Then you have FeCO42 negative. Right? Now here they are asking you strength of MC bond. See one thing. Simple is, it will be X is equals to +1, so it is Mn positive. This is nickel 0. This is chromium 0, neutral only it is. This is Fe2 negative. So definitely the one which has more electron density, if you calculate the electrons also, this will be Mn is nothing but it is 4s2 3d5. So this will become 4s1 3d5. Right? This is 4s. Firstly, if you talk about the positive and negative, I know that this is positive, so it will have least. This is negative, so it will have maximum. Right? Another thing is this is Ni, this is Cr. If you see this here, this is 4s2, 3d8. This is 4s2, 3d5. Right? Now, if you see this here, in this case, you have 8 electrons for 4 ligands. Here you have 5 electrons for 6 ligands. Right? So, here what you will see, the ratio says that you have more electrons here for this much ligands. Right? Okay? So, that's why, and moreover, not only this case, so you will say that this will have more MC strength. Okay? Ligands are carbonyl only. Okay, ligands are carbonyl only. We are only talking about carbonyl ligands, and this also depends upon the structure and all things, right? But as of now, you can say that why this is more. Now, if they ask you the strength of CO, that will be totally opposite. This will be the strength of CO. Okay? Sure. Then these are some of the structures directly from your NCERT. I have picked it. Like you have NiCO4. This is having a tetrahedral structure. Right? FeCO5. This is having trigonal bipyramidal structure. These are simple ones. CrCO 1, 2, 3, 6. This is having octahedral structure. Now this is important. Mn2CO10 has one Mn bond as well. This they can ask you. And this part is 1, 2, 3, 2, 3, 4. Yes, this one is octahedral. This part is also octahedral. Okay? Both the parts are octahedral. Right? Then, if you talk about this one, CO bond you have, right? And then 2 COR, 2 carbonyl are bridging, and 6 carbonyls are terminal. This is what they ask you. 1, 2, 3, 4, 5, 6, these are terminal. These two are bridging. And there is one CO bond as well. Okay? But that was last only. Okay? And this is your homework, guys. As you can see this over here, this is the homework, right? Okay? So I really advise you to do the homework, right? Rest is your choice, right? If you don't want to have the DPPs, this is the second homework question. Take the screenshot and that's it, right? So, in the end, how to remember DD transitions? In DD transition, it will look like this because of DD transition. If you don't have DD transition, it will look like this. Okay, that's how you can remember. DD transition, it will look like this. This is like D0 and D10. This is other. D2, D3, up to D9. They will have colored complexes. Right? Okay. So guys, this is our Vedantu JEE English channel, which you can subscribe to for all the updates regarding my lectures. And now I'm waiting for your homework, and write if that thing is absolutely clear, crystal clear in the comment section, and write down your homework. Let's see how many of you do that, right? Okay. So now the batch that you all are talking about, and guys, as I told you, freedom sale is over. Right? That's why I was telling you again and again, right? Today was the last day. Yesterday was the last day of freedom sale, right? So it's over now, right? You can see this here. Now the batch price is 4,999, right? And it will keep on increasing. So that's why I'm saying that even now you have time to get yourself enrolled into the batch, right? Get yourself enrolled into the batch because the classes are going regularly, mock tests, tattva modules, these quick revision cards, if I show you here, right? Everything is available and delivered to your home, right? Mock tests are being taken, whatever you need, everything is available, right? So what you need to do, you just need to click on this and click on this view course plans, and you will have different course plans here, and according to you can choose, right? Okay. So everybody, now I'll take your leave. Bye bye. Take care. See you all in the next class, and I'm waiting for your homework in the comment section. Bye bye.